Hi everyone, welcome back to Exam Ignite. Today I'm starting a new series of microcontrollers BE405 BEC 405A for the VTU 4th semester 2022 scheme. This is a module 1, part 1, where you will have a clear and topic wise handwritten notes here, and this will make you to have a better understanding and remember faster. So this is a part 1 video where I will be covering what is microcontroller and microprocessor difference, microcontroller and embedded processors, architecture, that is Harvard versus Princeton, and RISC versus CISC and 8051 architecture. So I have prepared these notes by going through the model question papers and previous year question papers to mark the important topics that are repeatedly asked so that you will know what exactly to focus on. So in the part 2 video, I'll be continuing with the input output pins and circuits and with the external memory interfacing. So here this is a most important question as it is asked in many papers, microcontroller versus microprocessor. Then RISC versus CISC is also important. Architecture, you have to learn the architecture and the explanation part. Then port 0 and port 3 are important, and also many of times all the 4 ports are also asked. So in the external memory interfacing, these are the types of interfacing of the ROM and RAM bits that was asked in few papers. So in this, I will be discussing in the part 2 the first one and the second one. So do watch the part 1 and part 2 completely. Microcontroller versus microprocessor. So how to write the difference? First write the diagram. That microprocessor, it contains a CPU along with RAM separately, ROM, IO, input output, timer, serial port communication port, along which is connected through the data bus and as well as the address bus. In the microcontroller, it has an inbuilt CPU, RAM, ROM, input output ports, timer, serial communication port. So to write the first difference, this contains microprocessor. It is actually contains only the CPU part. Here CPU, memory, input output, timer are all on the single chip. Here designer decides the size of the RAM or ROM and the how much input output to be handled. So here in the microcontroller, it has a fixed number. This is a Van Neumann architecture and that is an Harvard architecture. So microprocessor is a general purpose, like you can see in our main computers, it is used. So but the microcontroller, it is application specific, that is in the specific embedded systems it is used. So our microprocessor is of high speed and high cost, but microcontroller are relatively low speed and are low cost. So this requires more hardware to be interfaced. For that, it has less hardware. Power consumption is high, power consumption is low. So it does not support bit accessibility that supports. Example, you can go for 8085, 8086, Core i3, Core i5, Core i7 AMD processor. Here it is 8051 AVR and PIC ARM microcontroller. So next is the difference between Van Neumann and the Harvard architecture. So based on the parameters, we are going to differentiate them. Firstly, the diagram comes, the CPU and the data or the code memory are the code, it is extracted or sent or stored in the separate lines, that is address or data code. It is having only one address line and one data line for both the data and code memory. Here the CPU, for the data memory, it is having separate address and data lines. For the code memory, it is having separate address and code lines. Like data and code are stored in the same memory here, in the single memory, but here that is stored in the different memories. What is the memory type? It has RAM for data and code, but here data memory is for RAM and the code memory is for ROM. Buses, here you can observe there is a common bus, either it is in the address or in the date, but here it has having a separate bus for the transmission. Next is program execution. Code is executed serially and it takes more cycles, but here code is executed parallelly, that is parallel work takes place with the data so that there is a less cycles. Here data or code is taken in one cycle, therein in both the cases either the data or the code should be taken in one cycle. Next come control signals are less here, more there. Space is less here, more there, and cost is also less here, it's more in that. Next comes the difference between RISC and CISC. RISC and CISC based on the parameters. RISC is reduced instruction set of computer and CISC is complex instruction set computer. Instruction size in the RISC is fixed. Here it is variable. instruction fetch time, that is what amount of time is required, it is same for all the instruction in the RISC, but here it depends on the complexity of the instruction. Then here instruction set obviously reduced, so it is having the small and simple set. Here complex, so it is large and complex. Address modes, here less modes, as most of the instruction are based on the registers, but here more modes we need, as we are having complex instructions. So number of registers we use are many here, and here it is few. Compiler design is simple because it is reduced instruction. Here it is complex. Next comes program size. Program size is long here in the RISC and small in the CISC. Number of operand is fixed here, and here it is variable. Next, control unit. Control unit here is hardwired control. Then it is microprogram control. Execution speed in the reduced, it is fast. In the complex, it is slow. Pipelining here, it is more effective. There it is less effective. Processor, it is more suitable for the dedicated operation. Here, and there it is more suitable for the varieties of operation. Next is microcontroller for an embedded system. So an embedded product uses a microprocessor or a microcontroller to do one of the tasks or to perform any one particular task. So only one application software is burnt into the ROM directly. So a PC, in contrast with the embedded system, can be used for any number of applications. So it has a RAM and an OS that uploads a variety of applications. PC has various embedded products, so each one has a microcontroller inside to perform one task. So what are the criteria that we have to consider for choosing a microcontroller? This was asked in one of the paper, like what criteria you have to consider. So firstly, you have to check the speed of the microcontroller, how fast it is, what is the power consumption of it, what is the amount of RAM and the ROM on the chip, then number of input output pins, and timer on the chip. What is the packaging? Is it easy to upgrade to higher performance? Cost per unit time? Then comes availability of the software development, that is compilers, assemblers and debuggers. Then wide availability and reliable sources. So 8051 has the largest number of suppliers, that is Intel, Atmel and many of the other things. Next comes our main thing, the architecture. That is my 8051 microcontroller hardware. It belongs to the family of 8031 to 8071, and it is available in the two formats, that is NMOS and CMOS, that is N-channel metal oxide silicon and complementary metal oxide silicon. It is a 40-pin DIP, that is dual input pin, input output pin. So firstly, you have to write the block saying arithmetic and logic unit connected to the registers A and B. We are having PC and DPTR, which is connected, both of them are connected to PSW. We are having some special function registers in the RAM. So this is an 8-bit address line and this is a 16-bit address line. And we are having one ROM. Other things, we are having latches, 4 latches connected to the 4 ports. And finally, that is sent to input output A0, A7, D0 to D7 to the address line. Based on these ports, we'll be discussing further. Also, we are having enable ALE, PSEN, then XTAL, reset, VCC, and ground. Along with register banks, we are having 4 register banks. Special function registers like IE, IP, PCON, SPUF, SCON, TCON, TMOD, TLO, THO, TL1, and TH1. These are all we'll be studying in the third module. So it's a port 3 memory controller is connected. And finally, this is the internal structure of the RAM structure. Then this is our 8051 block diagram, which you have to write for the architecture part. So coming to explanation part, unique features of the microcontroller, it is an internal ROM and RAM, I/O ports with the programmable pins, then timers and counters are present, serial data communication. What are the CPU components? It has an ALU, working registers and the clock circuits. Some of the special features we are having here is 8-bit CPU with a register A, that is accumulator, and with a register B. We are having 16-pin program counter and as well as the DPTR. And we are having 8-bit SP, that is stack pointer. Internal ROM, or you can say EEPROM, that is electrically programmable ROM. Read-only memory, the 8051 of 0 and 8031. 2, what we are having in the 8051 is 4K. For the internal RAM is of random access memory is of 128 bytes. So that consists of 4 register banks. Each are having 8 registers. So 16 bytes may be addressed at the bit level, 80 bytes of the general purpose data memory, and 32 input output pins has arranged as 4 8-bit ports, that is P0 to P4. Sorry, P3. Two 16-bit timer or counter, that is T0 and T1, full duplex serial data receiver or transmitter, that is our SPUF. Control registers, we as I said, TCON, TMOD, SCON, PCON, IP and IE. Two external and three internal interrupt sources, oscillator and the clock circuits, one serial ports, one microsecond instruction cycle of 12 megahertz crystal, binary or data arithmetic, direct byte or the bit addressing. To explain the architecture part, this was about the special features of the ECE of microcontroller. Now, specifically explaining the architecture, what explanation you have to write for the diagram is it consists of a CPU, that is two kinds of memory section. One is for the data memory, we have RAM, and for the code memory, we have ROM. The input output ports, control logic, serial port, and the interrupt function. It has an internal data bus that is 8-bit controls that connects all the elements throughout the chip. So CPU, it monitors and controls all the operation that is performed by the microcontroller. It is having an 8-bit ALU with the registers like AB and PSW. We are having stack pointer, which is 16-bit program counter, and DPTR, data pointer register. It consists of a function, register, and a control unit. My memory unit, we are having two. One is ROM and RAM. ROM is 4K bytes on the chip memory. Non-volatile memory, this is RAM is 128 bytes of internal RAM. Volatile memory, it has 32 working register, that is of 4 register banks, as I said, bank 0 to bank 3. Each bank is having 8 registers, that is what R0 to R7. So there are 128 addressable bits in the internal RAM. Input output ports, it has 4 8-bit input output ports, P0 to P3. All the ports are general purpose ports, so we will be learning in detail next. P0 and P1, these are all multiplexed with address and the data bus. P2 is for the higher order bit address. P3 is for multifunction. Next comes interrupt control. Here it supports internal and external interrupts. So timers, it supports the two multiple modes, that is 16-bit timer or counter. Timer mode, it is used to generate the delay. Counter mode, it is used to count the external pulses. Serial port, serial communication at the RXT for the receiver and TXT for the transmitting. Oscillator, it provides clock, that is 8051, and decided baud rate for the serial communication. So here, this is our programming model of the 8051. Here are the registers. It is this B register, and we are having IP, IE, TMOD, TCON, THO, TLO, counter, TH1, TL1, SCON, SPUF, PCON, PSW. These are serial data registers. We are having stack pointer, SP, and this is our register banks in the left, and here we are having data pointer, PC, then P0, P1, P2, P3, finally internal ROM, 8051 program model. So this is our pin diagram of the 8051. Here we are having, firstly in the top we are having port 1 pins, then here we are having port 0 pins, here we are having port 3 pins, and here we are having port 2 pins. This is a dual input pin assignments. Explaining the registers, A register, it is having an 8-bit register and it is called as an accumulator. It is used to store the results, that is arithmetic operations of addition, subtraction, multiplication, division. It is used to store the result, that is logical, rotate, priority check, and testing. We will be learning this in the second module. 8-bit register, it is used to network and multiply, divide the operation. Then comes DPTR, it has a higher byte and the lower byte. DPH, DPL, old 16-bit address, serves as base register, indirect, jumps and lookup table, and external data transfer. It does not have any single internal address, that is DPH is for 83H and DPL for 82H. Both of them comprise to make a DPTR of 16-bit. 8-bit plus 8-bit. PC program counter 16-bit holds the memory location from which the next instruction has to be fetched. Next comes PSW. Here program status word, or you can say flag register. It is an 8-bit. So 8-bit, firstly, CY stands for carry, AC stands for auxiliary carry, F0 is our user flag, RS0, RS1 and RS0, these are our register flags, OV is my overflow, and one is reserved, and the last one is parity flag. So these are the things that are present in the PSW. So firstly, let me start with the CY, that is carry. It is set when the overflow of the bit 7 in the addition and in the borrow for the subtraction part. Let us take an example. We are having 99H and 90H. Write it in the form of 8-bit. So 9 can be written in the 804 8421 format you have to write here. So 99 can be written as 1001 and 1001. 90 can be written as 1001, 9 for this and 0 for this. On adding, I'll get a carry. So now CY will be set to 1. For the auxiliary carry, to set 1, when the carry from the lower nibble to the higher nibble, that is 9H and 9H. So here you can observe AC will become 1. Then we are having F4, that is general purpose. When it is 0, 0, it is bank 0, 0, 1, bank 1, 1, 0, it is bank 2, and 1, 1, it is bank 3. Then overflow flag, it is a result of signed number operation to largest set 1. P is parity flag, which checks the number of ones in any result. If it is even number, then the parity flag will be 0. If the number of ones is in odd number, then you can see the parity flag is 1. I hope this video was useful, and make sure you watch it if you have not understood any part, and please do watch the module 1 part 2 videos, and don't forget to like, share with your friends, and subscribe to the Exam Ignite for the next modules video and important questions and more VTU focused content. So thank you so much for watching.